All right, so here we go for the note card. Okay, so let's start off. We're just gonna go through this, by the numbers, one step at a time. So, we've got those pesky equations that we need to break down into amplitude, period, phase shift, vertical shift, reflection or not. And then we also have those graphs that we need to pull out the amplitude, find the period, and then write the equation for. So those two things kind of go hand in hand. We're doing a lot of the same things for it. So let's just make sure we define a couple of these terms and then think about what you want to put on your note card. So amplitude. Amplitude, well, real quick, midline. If we're talking about the graph, so let's be specific about like this graph right here. The midline is just the halfway point or the halfway line. It's the middle of your graph. Okay. So the amplitude is the distance from the midline to your highest point or the midline and the lowest point of your graph. So like for instance right here, this is a sine graph. That is my midline. And so the distance from the midline to the highest point of my graph is 3. So this has an amplitude of 3. Or the distance between the midline and the lowest point of the graph is 3. So my amplitude is 3. Okay. Amplitude is something that's visible on or in my equation. Okay. So we definitely want to know amplitude. Next is frequency and period. Period, right, is the length that it takes for me to get through one cycle of my graph. So remember when we're talking about sine graphs, it looks like that, and when we're talking about cosine graphs, it looks like that, right? Or something to that effect. Okay. Well, frequency is how many cycles or wavelengths I can fit between 0 and 2 pi. So let's go back to the graph real quick. So like for instance, this graph between 0, between 0 and 2 pi, I'm only getting half my graph, right? That's the whole cycle. So my frequency for this one will be 1/2. It's half. Now for this one, I've got one sine graph cycle that goes from 0 to pi. I've got 2 cycles that goes from 0 to 2 pi. So in this case, my frequency will be 2. Well, I need the frequency to write my equation. Okay, so when I'm looking at the graph and I want to write the equation, I kind of need my frequency. So you would think the frequency would be there. It's not, so whatever. So anyway, if I look at this, frequency. Also, frequency helps me get my period. Well, in this case, I can see that period, what is the length that it takes me to get through one cycle? Well, in this case, it's pi. So boom, that was easy, pi. In this case, one cycle, it takes me to get 4 pi to get it. So that's how I can get my period there. If you can't use a visual like this to get your period, in the case where you have something like this, then what you do is you take 2 pi and divide it by your frequency, and that is your period. Okay? So like what is my frequency here? Well, let's look at this. Here's pretty much the standard standard setup for the equations that we're dealing with. So y equals a, that's the amplitude, sine or cosine, then b times, now I got b times x. X is, it's just for, sine or cosine or whatever I'm taking of. So the b, the number that's being multiplied times x, that's my frequency. Okay. And then I've got, if it's in parentheses, minus or plus some whatever, right? Um, then that is my horizontal or my phase shift. I don't know why they call it horizontal shift when they should have called it phase. Should have just called this phase shift. So phase shift, that's my horizontal shift, and then vertical shift. The the phase shift is inside the parentheses. The vertical shift is outside. Okay. So now let's take, I would suggest writing this equation, all of this, and also making a note, say period equals 2 pi divided by the frequency. Okay. So if I'm trying to find a period like this, well, according to my setup here, B, that's the frequency. And so it's 2 pi divided by 1/2. And what kind of a problem is that? Yeah, that's right, Makai. That is a keep change flip. So 2 pi divided by 1/2. So that's 2 pi times 2 over 1. So that's 4 pi. Now see, the same thing happens here. My frequency is 1/2. I'd say 2 pi divided by 1/2 and I get 4 pi. Boom. Okay. Now, again, with my phase shift, that would be something like this right here. So I've got x minus pi over 4. Notice the equation though. It's minus c, and that's my phase shift. So in this case, since the format is minus c, this one is pi over 4. That is my phase shift. Now I don't have a vertical shift because the vertical shift is after that, so nothing. Reflection means my stuff has to be negative, right? Okay, so the reflection is none or NA. This one is negative. Now, it's important to know that the number in front, that's my amplitude, but it's distance. So distance is never negative. So amplitude is always going to be positive. So this is going to be amplitude of 2. The reflection is yes, right? And then the number that's being multiplied by my x, that's my frequency. So in this case, my frequency is 1. In this case, my frequency is 1/2. In this case, my frequency is 1. In this case, my frequency is 1. So now I look at the number that's in the parentheses, right here. So this one, my phase shift would be pi. In this one, my phase shift would be 3 pi divided by 2. So I know I'm kind of jumping all over the place, but the main thing is just so you can have, suggestions for your note card. So I would suggest you put this on your note card. Definitely want to understand what this represents and what that represents. So you can do this here or here. I guess I don't see the need to go through every little thing that we went through. If you want to know how to use this stuff, how to solve these problems, just look at the video that I did before. Okay. So that's the first thing there. And there's the second thing here. Remember, this is y equals, so A, that's my amplitude. My amplitude in this case is 3. So I got 3. This is a sine graph. It's that we're z. So I would also say maybe you give yourself, a couple of, some pictures of what the sine graph and the cosine graph look like. So right there, so that's the sine graph. And then the frequency, that's my B, the frequency is 2 because I've got 2 graphs between 0 and 2 pi, or 2 waves, or 2 cycles. So that's 2 and then x. There is no phase shift or vertical shift in this case. And I don't think you're going to see one, but hey, whatever. So there you go. So I would write this down. So next, let's talk about exponent rules. So we've got the multiplication property, the power property, the division property, the zero property, and the negative exponent property. Right? So let's just do this one by one and then we'll relate it to this. So I would suggest that you list all of these on there in some way, shape, or form, however you want to write it. So the multiplication property, add your exponents if the bases are the same. So let's make this a little bigger. Okay, so in this case, I've got 3 to the third power times 3 to the fifth power. If I'm multiplying and the bases are the same, I just add the exponents. What the heck? Okay, yeah, that's not good. Yeah, we're going to take a pause on that. Okay, let's try this again. Erase this. Let's try that one more time. Okay, so 3 to the third power times 3 to the fifth power. 3 to the eighth power, because I just add the exponents. Or if I got a variable, it works the same way. X to the second power times x to the 10th power. X is my base, 2 plus 10, so that's 12. Boom, I'm done. Right? So if I've got something like this, right, which is something like this, I've got the 2 and the 4, so I'm going to break that down piece by piece. 2 times 4 is 8. I've got x to the second power and x to the third power. My base is the same, it's x. I add the exponents, that's 5. So look at 5. I've got y with no exponent, which means it's y to the first power, and then y to the fifth power. I'll multiply those, that's y to the sixth power. Boom, I'm done. Okay, so that's the multiplication property. Power property. I like the way this thing says. It says multiply exponents when they are inside and outside of parentheses. So it's like this, right? So I've got x to the third power all taken to the fourth power. That's when I multiply. That's 5 to the 12th power. Right here it works with variables too. Y to the third power taken to the 11th power. That's y to the 33rd power. What about this? I have to take everything in here to the fourth power. Okay. So that means I'm going to have 6 to the fourth power. I'm going to have x to the fourth power taken to the fourth power, which is x to the 16th power. Then I'm going to have y to the 8th taken to the fourth power. That's y to the 32nd power. And then z, there's no number, so it's a 1. So z to the fourth power. All right. Division property. Subtract top exponent minus the bottom exponent when the bases are the same. So it's important that the bases are the same. So in this one, I've got 3 to the 12th divided by 3 to the 5th. So that's 3. 12 minus 5, so that's 7. Think of the line here, that divider line, is like a minus sign. So 12 minus 5. In this case, that is y, that's my base, 17 minus 6, 11. Well, I want to look at these here because negative exponents play a part. Now, we're not going to talk about the negative exponent property yet, but I want to hit trying to do these. Okay, so like for this problem, I'm going to take it piece by piece. I've got negative 6 times 4, so that is negative 24. I have a to the negative 3 and a to the 8th. So like I was saying earlier, what I think you should do is, okay, so a is my base. I'm going to take negative 3 plus 8. I'm going to write that down so I can see it and say, okay, negative 3 plus 8, that's a positive 5. And then I'm going to have b. Well, there's only one b. There's just this one, b to the negative 2, so that's b to the negative 2, right? And we'll come back to that in a second. So let's get to these other ones. Zero property is easy. Anything to the zero property is 1. So if you got parentheses and you got something to the zero property, it's still 1. So when you got a problem like this, that's 3a squared b to the fourth, all taken to the zero power is 1, I'm done. But see if you got something like this, to where I've got something inside parentheses that's to the zero power, but the 3 is on the outside. All of this is 1, but that 3 is on the outside. So that's 3 times 1, or 3. So you want to be careful about stuff like that. Okay. All right. So next, let's talk about the negative exponent property. The negative exponent property, what does that mean? Well, if I have 3 to the negative 4, if the exponent is negative, move the term to the opposite side and make the exponent positive. Opposite side, that's probably a weird way to say it. I'd say we take the reciprocal. So if this is 3 is a whole number, I'm going to make it 1 over 3. And now the negative disappears and I just got to the fourth power. Right here, x to the negative 6, I'm going to make it 1 over x, and now it's just 1 over x to the 6th power. So this one right here, you always simplify your fractions. So I've got 16 divided by 2. Well, 16 divided by 2 is 8. Then I've got x to the negative 10 divided by x to the negative 2. Well, it's just like I told you. That is negative 10 minus a negative 2. See, this is why I want you to write it out. Just on a scrap sheet of paper, write it out so you can see, wait a minute, that's negative 10 plus 2, because when you subtract the negative, you're adding a positive. So that's going to be x to the negative 8. Now that I have this negative, I'm going to make that 8 over x to the 8th power. See, because the negative exponent is only worried about the 8. There's no parentheses there. So I'm going to move the 8 down. I'm going to take the reciprocal of x and then make that the negative exponent goes away, and I've just got the 8. So now let's look at one of these, how this works, right? So right here. So I got 16 over 24. I can divide those by 8, so that's 2 over 3. I've got x to the 12th divided by x to the 6th, 12 minus 6. So that's just x to the 6th. Right here, I've got 6 y to the 6th divided by y to the 11th. That's 6 minus 11. So that's y to the negative 5th power. And then last, I have z to the negative 3rd minus or divided by z to the negative 4th. So that's negative 3 minus a negative 4. That's negative 3 plus 4. So that's going to be z to the 1st power. Now, I want to write this as positive exponents only. So that's going to be 2 over 3, x to the 6th, y to the 5th down there, z to the 1st. So you want to write down, and somewhere on your card, these properties for exponents. The multiplication property, the power property, the division property, right? The zero property and the negative exponent property. Now, there's one more property we need to talk about, and that is the fractional exponent property. So that is in here on our little cheat sheet. So it's right here. So what does this fractional exponent mean? Well, the numerator, that's my power. And then the denominator, this is my root for my radical. So then let's do this one. So this one to the 4/7 power, the 7th is my root. So that's the 7th root of 3mn taken to the 4th power. Now that is the correct way. The incorrect way is the 7th root of 3mn to the 4th, because that 4 only applies to the n. It doesn't apply to everything. And as you can see, those parentheses mean that 4 has to apply to everything. Okay? This, bad, that, good. You could simplify it and say I want the 7th root of 3 to the 4th power, which I know is 81, m to the 4th power, n to the 4th power. So either one of those is acceptable. That is not. That is wrong. Okay? So you want to make sure that you got all your rules. Fractional exponent. That is your power. This is your root. All right. And like we were saying for the powers, the power rule, everything in the parentheses is taken to this. So what happens with the second one? That is a perfect example of being able to use the power rule. So let's do that. So right here. So I'm going to have the ninth root of 7ab to the fourth to the second power. So now if I want to simplify that, that is the ninth root of 49, because that's 7 to the second power, a to the second power. And then here's where the power rule really comes in, b to the fourth taken to the second, so that's b to the eighth. So you want to make sure you got those the exponent rules down, okay? Fractional exponents, dividing exponents, the property for exponents, the negative exponent property, and power and the product property, or multiplication product, or sorry, multiplication property. So next we got logs. So logs, we actually have several rules. Okay, so for this right here, we've given several of these names. So this one is called the product rule, because if I have a log that has a product, I can separate it. This right here is the power rule, because if I have a log of some number that has a power, I can pull that power out and have it multiplied by it. And then this one right here is the quotient rule, because we're dividing. So I've got a log of something that I'm dividing, I can separate that. So why do I care about those rules in relation to like evaluating? Well, right here, log of 36, I can make that a product. So that's log of 4 times 9. Or I could have said that was log of 6 to the second power. Right? So what do I got next? Well, here I can say that's log of 4 plus log of 9. Or this is 2 times the log of 6. There's a couple ways you could do this. Right? So I'm using these rules. Well, according to this chart, I got 2 and 3. These ain't 2s and 3s. But 4 is 2 to the second power. And 9 is 3 to the second power. Or what about 6? Well, 6 is 2 times 3. So I'm using the product rule, the power rule, and the quotient rule for logs to rearrange these problems, to stretch them out, condense them, or whatever I need to do to solve them. And I'm going to use these things here in my chart. So it's important that you know that you write down these rules, that you know them. So I'd write them on my note card. All right. I'd write all these rules. This is on page 86, I believe, of your math book. That's in lesson 12 if you want to look at it. So I will write these rules down. Those rules are also applicable to this right here, to these problems, also to condensing or to expanding. So condensing, I'm going to take something that looks like this and I'm going to make it look like this. Expanding, I'm going to take something that looks like this and make it look like this. So we're using a product in the quotient rules for that. And then if we try to sneak by something that looks like this, we're also going to sneak in the power rule, right? So like for instance, this one right here, this is log base 3 of x squared plus log base 3 of y plus log base 3 of z. And then that power rule, so that's 2 times the log of base 3 of x plus log base 3 of y plus log base 3 of z. Using the product rule and the power rule. And I could do something similar to this. I've got the product rule and the quotient rule. So that's log base 4 of x times y minus log of base 4 of 3. And then I need to do the product rule here. So log base 4 of x plus log base 4 of y minus log base 4 of 3. Now there's one more thing that we want to write down as far as logs go. You want to make sure you understand exponential form and logarithmic form. So if I took, let's take one of these, like this one for instance. So let's say we're looking at log base 6 of 216. We're going to say that equals 3. That right there is just it's a complete equation, a logarithmic equation. So that's logarithmic form because basically it's got log in it. Exponential form doesn't have log in it. It's just got exponents. So 6 to the third power equals 216. So here's exponential form. Here's logarithmic form. These things are basically the same. They're like reversing your situation. So you need to be able to go from exponential form to logarithmic form or logarithmic form to exponential form. That's why when we were doing these, I was practicing like this. So I took this log and I said that was 5 to the third power and that equals x. So I went from logarithmic form to exponential form and then I solved for x, right? Okay, or this one, this is x to the third power equals 64. Again, I'm taking log rhythmic form and I'm changing it to exponential form, and then I'm solving it. X equals 4, because 4 to the third power is 64. So you need to be able to change between the two. If I have, say, an exponent, like 5 to the third equals x, then I know this is my base, that's my exponent, and this is called my argument. Log base 5 with an argument of x equals an exponent of 3. You need to be able to switch between the two. So I would highly suggest you make sure that you know this stuff. Put on your note card. Okay? Exponential form and logarithmic form. So that's all of these. So now let's look at this right here. This right here. So now we're going to talk about SOHCAHTOA. So what is that? What is that? Well, that is a little acronym that we use to say sine equals opposite side over hypotenuse. I think I spelled that wrong. Hypotenuse? Maybe not. Okay. And then cosine equals adjacent over hypotenuse. And then tangent equals opposite over adjacent. All right. So if I look at this right here, so sine of 60, that's the opposite side over hypotenuse. Cosine of 60, that's the adjacent side over the hypotenuse. Now, I believe when we were talking earlier, when I was talking about tangent, I said do sine over cosine. Well, I forgot, we're all human. I forgot that SOHCAHTOA says if I was doing tangent of 30, I can say the opposite side, which is 1/2, divided by the adjacent side. So you get the same thing, you know. So this problem is 1/2 divided by square root of 3 over 2. So if I say sine of 30, it gives me 1/2. If I say cosine of 30, it's square root of 3 over 2. Or I can say opposite over adjacent, same difference. So I would suggest writing that down. I would also write down, well, let's get to this first. So now let's talk about this, the unit circle. So if we're doing something like sine of pi over 3, you're going to be this problem, this diagram is going to be on the test, so you don't have to worry about writing this down. But maybe you want to write yourself a few notes on your card. So anyway, sine of pi over 3. So pi over 3 is right here. Sine is the second coordinate. Cosine is the first. So sine of this one is just square root of 3 over 2. When I'm looking at cosine of 5 over 6 right here, cosine is the first coordinate. And notice that little negative. So that's negative square root of 3 over 2. So now I'm at tangent of 3 pi over 4. 3 pi over 4 is here. Tangent, again, tangent is sine over cosine. Well, see, I don't have the benefit of other stuff, so I'm going to take right here my sine and cosine. So that is my sine is the square root of 2 over 2. And then my cosine is negative square root of 2 over 2. So like I said before, this is like saying 5 divided by negative 5. Well, that's just going to be negative 1. You know, these things are identical, so they cancel each other out, but the negative still left over. So that's going to be negative 1. So the 6 trigonometric ratios, we got sine, cosine, tangent, cosecant, secant, and cotangent. So why am I telling you this? Well, I was thinking about adding this on the test. This wasn't on the test. I was going to add it, but I changed my mind. But what I might do is maybe put 1 or 2 extra credit problems on the board just for the heck of it. So you might want to write these down in that case. So sine and cosecant are inverses of each other. So sine is 1 over the cosecant, and cosecant is 1 over the sine. Now, what the heck does that mean? Well, if I say I want to know the cosecant of pi over 6, so I look for pi over 6, it's right there. Remember, these are sine and cosine. Well, I know that the cosecant of pi over 6 is equal to 1 over the sine of pi over 6. So, see, this diagram tells me that, so pi over 6, the sine is 1/2. So then this problem is going to be 1 over 1/2. And Stephanie, what kind of a problem is that? That's 1 divided by 1/2. That's a keep change flip. 1 divided by 1/2. That is 1 times 2 over 1 or 2. So anyway, cosine is the inverse of secant, and secant is the inverse of cosine. And tangent is sine over cosine, and cotangent is cosine over sine. So I would suggest, excuse me, writing these down. Now, you may not really need these except for maybe an extra credit problem, but it never hurts to be on the safe side, you know? But we use this definitely. So you want to have at least these things on your note card. If you're going to do your note card, that is. All right, so next. What do I know about this here? When I'm dealing with complex numbers with A plus BI form. Now, what the heck is that? Well, A is my real number. BI is my imaginary number. Okay? So, in this case, when I'm adding, I just do like terms. I take my real numbers and combine them. I take my imaginary numbers. Oops. my imaginary numbers and combine them, right? So that's going to be 7 plus negative, so that's a positive 5i. Now, in this case, when I'm multiplying, you don't worry about like terms until the end, until after you're done with your multiplication. So I'm going to use FOIL for this. So that's 7 times 4, my first terms. First is 7, first is 4. So that's 28. Then I've got my outer terms. My outer terms are this 7 and this 7i. So 7 times 7i, that is 49i. Then I have my inner terms. That's the 4i and the 4. So that's 16i, you know? And then last terms, my 4i and my 7i. That's going to be 28i squared because I times I is I squared. Now you need to remember that I equals the square root of -1 and I squared equals -1. So when I multiply this all out, now I'm going to add like terms. First I'm going to add my i's. So 28 plus 65i plus 28 times I squared. Well, I squared is -1. So that's 28 plus 65i plus 28 times -1. Well, that's going to be 28 plus 65i minus 28. And then finally, the positive 28 and the negative 28 cancel each other out. So I got 65i. Now, a plus bi is the form. Well, what am I doing here? I just got 65i. That's because my a is 0. You don't have to write the 0 plus, okay? You don't got to write that. But that's understood that that's what that means when we're talking about a plus I, okay? So that's that. And then finally, we've got the equation of a circle. So in a circle, as far as an equation goes, works like this. So this is the equation of a circle. So you'll want to make sure you got this written somewhere. So if this is my equation, the center of that circle is h and k. That's my x coordinate, that's my y coordinate, if we're talking about in 2 dimensions, of course. And it's in this format, x minus h, y minus k. That's where I get my h and k from. And then my radius for my circle is just r. Well, if this is r squared, if I want to get r, I want to take the square root of r squared. So now we're going to put that in the context here. So if I've got something like this, right? This first one, I look at my general equation. Well, I don't got an h. I don't got a k. Well, that's because there's 0. So my center would just be 0, 0. That's my center. So then what about my radius? Well, my radius is the square root of this number. So the square root of 144 is 12. So my radius is 12. What about this one? Well, my center, h, x minus h, x minus 3. So that's 3. Y minus k, y minus 4. So that's 4. So notice those are minus, and that's where I get my positive values from. It's almost like I got to take the opposite of what I see there. Okay? And then my radius for this one, square root of 25 is 5. Now this, you know what, let's do this one first. So right here, what's my center? Well, my center, x minus h, x minus 12, so that's 12. Y minus k, y plus 5. Remember, when I'm doing this, you can think of it as like I'm taking the opposite of the number that I see. So minus 12, that's positive 12. Plus 5, that means I'm dealing with a minus 5. Well, just so you can understand, I'll write this out. So if I'm telling you that the format is y minus k, and I've got y plus 5, that doesn't look like that. But if I change y plus 5, and I'm trying to get it to look like y minus k, if I say y minus a negative 5, See that those two things are the same. Y plus 5 is the same as y minus a negative 5. And y minus a negative 5 is that format, y minus k. So that's why we got a negative 5 there. And then I've got my radius, which is the square root of 169 is 13. So last but not least, what about this problem? Well, oh no, there's no h. That's because h is 0. If I got x minus 0, that's just x. And x squared is x squared. So for my center, that's going to be 0 for the x. And then y minus k, that's going to be 8. And then my radius, well, I got to take the square root of 38. Well, wait a minute. What's the square root of 38? Is the square root of 38. And we're going to call it. Some radicals you can simplify. I'm not worried about you simplifying them. Just making sure that you understand that the radius is the square root of whatever this equals. So there. That's pretty much everything that if you were going to put something on your note card. Let's see. Let's double check real quick to make sure. Oh, you know what? Let's almost forgot. Right here for our scientific notation. Now there's not really a general form for scientific notation. So what I would suggest is just write down a couple of examples. You can write whatever you want on your note card. So just give yourself a couple of examples if you need to. So this is standard form, right? And so scientific notation is 1.785 times. Now I know that my exponent is going to be negative because this number is less than 1, 0 point. So how many moves did I make? 1, 2, 3, 4. So that's a negative 4. Well, what about 186,000? Well, that number is bigger than 1. So I know that my exponent is going to be positive. So I look for my significant digits. That's 1.86. How many moves did I make to get the 1 in front of the decimal place? 1, 2, 3, 4, 5. So that means I'm going to have times 10 to the 5th power. So now what if I want to go from scientific notation? So let's say that is 1.9 times 10 to the negative 4. And I want to go to standard form. So I got my 1. I'm moving the decimal place. So I move my 9. So how many moves do I got left? Oops. That's the wrong way. So let's try that again with the right way, right? Okay. I said it the wrong way, so I want to make sure I say it right. So here's my decimal point. The exponent is negative, so I know that I'm less than 1, so I'm going to the left. So I'm going to write my 1 and my 9 down. The decimal place was here. I moved it here. So that's one move. How many moves do I got left? That tells me how many zeros I got. I got 3. 1, 2, 3. So that's my standard form. What about 4.54 times 10 to the 9th power? So standard form, that's 4. And then I've got 5, 4. I move the decimal place twice because that's positive. I'm moving to the right. So that was 2 moves. I got 7 moves left, so 7 zeros. 1, 2, 3, 4, 5, 6, 7. Eh, eh, eh. So what is that? 4,540,000,000. So there you go. So I would say that's pretty much everything. Give yourself a couple of examples. And honestly, it works the same with this. Maybe you don't want to just write down this thing. Or maybe in addition to writing down that thing, you say, you know what, Ferg, I'm going to write down this whole thing. So I'm going to solve this problem and I'm going to write it down. So this one, it's got a negative up front, so the reflection is yes. The amplitude is 1. It's a sine graph, whoop-de-doo. The frequency is 1. All right. So then what's the period? That's 2 pi. And then my phase shift, because that's plus pi over 2, that's a negative pi over 2 for my phase shift. And then my vertical shift is 1 or plus 1. And then to make things interesting, I'll give myself another one. Well, y equals 4. 4 is my amplitude. My frequency is 1, so my period is 2 pi. My reflection is no. My phase shift is 3 pi over 2 because remember, it needs to be in the form of negative whatever. And then my vertical shift is nothing. Now this one right here has a frequency. So I've got y negative sign, so that's a yes for reflection. The amplitude is 1 because there's no number there. My frequency is 1/2. And then remember my period is 2 pi divided by the 1/2 or divided by my frequency. So that's the keep change flip, right? Right, Nishala? So 2 pi divided by 1/2, 2 pi times 2. So my period is 4 pi. And then my phase shift is nothing because there's nothing in parentheses, but my vertical shift is 3. So maybe you give yourself an example or two. Now you got all the space on that note card. So you can write whatever you want to write. So write general examples or specific examples, whatever helps you out. All right, so those are my suggestions for your note card. All right, see you tomorrow and good luck.